Okay, so what we want to do today is consider our sampling distributions. All right, so we're going to start off with the population of interest. We'll call that our original population. Okay, this population has a probability distribution, a mean, variance, standard deviation, and proportion. Okay. Now, what we want to look at is what happens when we collect samples from this population. Okay. So, let's suppose we collect ourselves a sample. Now, we can calculate our typical sample statistics for this sample, such as our sample mean, variance, standard deviation, and proportion. Now, the problem with samples are every time we collect a sample, we get a different value. So suppose you collected a different sample than the one I just collected. And so you collect your sample, and now from your sample, you calculate your sample statistics. Again, x bar, s, squared, s, and p hat. Okay, but those aren't the only possible samples. Someone else could have gotten a completely different sample than the ones we got. So if they collect their sample, and they calculate their sample mean, variance, and standard deviation, and so on and so on, and we could consider every possible sample, and each one of those samples would have its own set of statistics. So really what we have here is hidden behind the scenes, we have this hidden population of x bars. We have a population of sample variances, a population of sample standard deviations, and a population of sample proportions. That's a lot of populations hidden behind that original one population. What we want to do is carefully consider the aspects or properties of these distributions. For instance, each one of these populations of cells has all the properties that a population would typically have. So for example, the population of sample means has its own probability distribution, its own mean, variance, and standard deviation. The same thing goes for the population of sample standard deviations. And the population of sample standard deviations has its own distribution, mean, variance, and standard deviation. And finally, the population of sample proportions has its own probability distribution, mean, variance, and standard deviation. Okay? So, even though when we collect a sample and we calculate, say, for example, x bar sample mean, that sample mean is random. But that doesn't mean it's not predictable. Okay? When we put all this together, we know that from each population we could sample from, there's a very specific set of possible x bars, and we know something about how likely it is to get those values, and we know something about the mean, variance, and standard deviation of those sample means, so we know a lot about the population of x bars, and s squareds, s's, and p hats, of course. So that means our sample statistics aren't these wildly unpredictable quantities, but instead they are truly random values, and as such, they have a structure that is predictable and usable. And this is what we need to investigate further.